Okay, we've not been very careful about normalizations. There might be 2 pi's and so on. I haven't been careful of how exactly normalize this, but the main point is that this expectation value is a thermal expectation value, where this beta is related, is 1 over T, and this T is the surface gravity by 2 pi. Okay. So it's related to the surface gravity of the black hole. So these were the points that we made last time, and then I said that Hawking said that if you take this outgoing radiation into account, then you would think that the black hole evaporates, and notice that this temperature depends only on the surface gravity, which depends only on for a spherically symmetric black hole, the kinds we were considering last time, only on the mass of the black hole. So you could take black holes with different kinds of compositions, and they would all evaporate into some gas of whatever particles there were, whatever fields there were in the background of the black hole, into a thermal gas which only seemed to depend on the temperature, or only seemed to depend on the mass. And because we think that quantum fields give us a microscopic description of what's happening, it would seem that the final state is independent of the initial state. Okay? So this leads to a seeming paradox. Can you see at the back? You can? Okay. Okay, so it leads to a seeming paradox. So these were the 4 points we made last time. And the seeming paradox is that, look, the outgoing modes picked up some expectation value that didn't know about what the black hole was formed from. And all these points are tied together. The reason the outgoing modes didn't care about what the black hole was formed from is because at late times you have this isometry, which is T goes to T plus delta T. And because the horizon is just like empty space, therefore you can apply quantum field theory, and it turns out that the outgoing modes don't have any information about what the infalling matter was, and that's why you get a seeming paradox. Okay, so are these points clear? These bullet points, at least, even if the details of all the calculations we did last time are not clear. If there are any questions about this, we can take them now before we go on to the next point that I want to make. Yeah.
What exactly is thermal?
Okay, so what is a thermal expectation value? So this is something in statistical mechanics. So thermal expectation value means what is the expectation value of something if you put it at a certain temperature. In quantum mechanics, the way that is defined is you define what's called a density matrix, which is e to the minus beta h by z of beta, where the z of beta is what's called the partition function. Have you seen this? As z of beta is given by trace of e to the minus beta h. And the thermal expectation value of an operator is then given by trace of rho O, where rho is this particular density matrix. Okay. This means that you allow, so what does this physically mean? Okay, this is the mathematical definition of the thermal expectation value of an operator O at temperature beta, at temperature 1 over beta. It's given by, you take this, are you familiar with density matrix? You take this density matrix and then trace it with some operator, and you get a thermal. And what does this physically mean? What this physically means is that the system has a probability of being in all energy eigenstates with a probability that's controlled by e to the minus beta e. Okay? So this is what you would call e to the minus e by kt. Okay, so beta, I haven't been writing the Boltzmann constant here, but so I wrote beta as 1 by t, but you could have written beta as, you could have put the Boltzmann constant. So what this is saying is that, the system is not in a given state. It could be in any of the energy eigenstates, but the probability of being in a given energy eigenstate is given by e to the minus beta e. And if you do that and you average over all possible expectation values you could get, then the average expectation value, or the expected value of this operator O, is given by this. Okay, that's what a thermal expectation value means. So it's the expectation value you expect for an observable at finite temperature, at a given temperature.
E was the outgoing, no?
Yes. This is the thermal spectrum for the outgoing modes. So this I explained last time. This is in fact the thermal spectrum that you would get if you took this H to be the Hamiltonian of a simple harmonic oscillator with frequency omega, and you computed this. This is the spectrum you would get. Usually, you smear these when you study the simple harmonic oscillator. You work with fields which are normalized so that b omega dagger b omega is equal to 1. Here we are working with delta function normalized fields. But apart from that caveat, which is actually not relevant, you can smear them to get fields which have canonical commutation relations. This is also the expectation value that you would get if you took a simple harmonic oscillator and put it at temperature 1 over beta. And that's why it's called a thermal expectation value. That's not how we computed it, But if you took a simple harmonic oscillator and did this calculation, you would get that answer. In fact, this is a good exercise to do. Maybe this is actually a good assignment problem. Okay, take the Hamiltonian. It's a good thing for all of you to work out. You should really work this out if you really want to understand anything about black hole information. Take the Hamiltonian for a simple harmonic oscillator, which I remind you is just given by h is equal to omega a dagger a. And you should never worry too much about the 0 point energy. It's not important in any of these calculations. And we set it to 0. So it's given by this Hamiltonian. Take this Hamiltonian and work out this expression, work out the partition function, work out this expression, and check that the expectation value of a dagger a is given by this. And you can also check that the expectation value of a dagger is given by the same expression, but with a 1 here instead of e to the minus beta omega. Okay, so this is actually a good exercise for all of you to do. Please try and do it. We're not checking assignments, of course, but I would strongly encourage all of you to do this exercise for a simple harmonic oscillator with this Hamiltonian, and then compute the trace of, with this rho of a dagger a, and the trace of rho a dagger. In fact, this is also important for the lecture that I think Ashok is giving, because when you count the entropy, you also count it by computing these partition functions. I mean, maybe I don't know, I haven't been for the lectures. I'd be computing a twisted partition function, but this is the basic kind of object that you try and compute. Okay, good. So, is this clear? Okay, great. So now, in fact, maybe this is a good segue into what I want to say. I want to spend much of this lecture on a statistical mechanics point. And the question I want to ask is, in this lecture, how close are pure and mixed states? And I'm going to explain what this question means. Okay. But this is the question I'm going to try and answer at the end of this lecture. Okay. So this is the title of this lecture. It's in fact, what I'm saying here is something which is simply simply just some physics about statistical mechanics that you should know independent of anything we say about black holes or not. Okay. So, and this is also related to later in this lecture, I'm also going to discuss the small corrections theorem that many of you have asked me about, and Professor Majumdar and others have also worked on, and many of you, I think, have also heard Samir Mathur speak about. So I'm going to discuss this also, but right now I'm just going to ask this question, which is a question in statistical mechanics. I'll explain what this question means. Okay, so in quantum mechanics, there are two kinds of states we can consider. For instance, imagine that you have Schrodinger's cat state, right? So you can have a cat which is alive, right? And you can have a cat which is dead. So you can have a cat which is okay. So this is a Schrodinger cat state. Okay. Okay, happy and depressed. Fine, that's also fine. Okay, happy and depressed cat. Yeah. Okay. So actually, why to kill the cat, right? Let's make the cat happy and depressed, right? So the cat is either happy or it's sad, right? And this state is an interesting state because it's a state which says that if you make a measurement of the cat, if you kind of ask the cat how are you feeling, then the cat will say with probability half that it's happy and with probability half that it's sad. However, this is not quite the same as saying that the cat is in either happy with probability half or with sad with probability half, and we just don't know. Okay, this is something that you studied in quantum mechanics. So I'm not going to keep drawing the cat. So instead, I'll call this state 1 and this state 0. Okay. And so let's call this state 1 by square root 2. Okay. This is an example of what's called a pure state. Even though if you make a measurement, so the cat was good for a joke, but for instance, if you make a measurement of sigma z in this, which in this case is like asking the cat if you're happy or sad. If you make a measurement, you will find with probability half that the answer is 1 and with probability half the answer is 0. So let's call this psi pure. But there is another way you could have achieved the same answer classically, which is that you could have said that this cat is deterministically either happy with or either in the state 1 with probability half or in the state 0 with probability half. And that in quantum mechanics is represented by what's called a density matrix. which is written this way. Okay. So this is called a density matrix, and what this density matrix means is that you have a probabilistic mixture of two states, the state 1 and the state 0. Okay? And the way you compute the expectation value of operators in this density matrix is, for instance, if you wanted to compute the expectation value of some operator O, then you would compute it as trace of rho mixed O. Here, if you wanted to compute the expectation value of some operator O, you would so let's call this O mixed. You would compute it as O pure is expectation value in this state psi pure. I'm going through a little bit fast, but I'm assuming that many of you have seen the notion of a density matrix and a pure state in these kinds of superpositions before. Is that a fair assumption or? Okay, good. So, in this state, this is how you compute the expectation value. In this state, this is how you compute an expectation value. By the way, you can write this state also in terms of a density matrix. What would the density matrix be if you wrote this state as a density matrix? Okay, it would be the outer product, right? So it would, you would have some cross off terms, some off diagonal terms as well. Now, if you look at a particular expectation value, let's say I look at the expectation value of sigma z, then sigma z has an expectation value which in this case is 0 because sigma z looks like 1 minus 1. Okay? So the expectation value of sigma z in the pure state is equal to 0. Okay, and the expectation value of sigma z in the mixed state is also equal to 0. So you might have said the mixed state and the pure state look the same. However, they don't look the same because in some states the expectation value of some operators can distinguish between this pure state and this mixed state. For instance, if you look at the operator sigma x, then this operator in this state has not only that, so it has what terms does it have? So this has some term which looks like 1 sigma x 1, and there's a half which I'm plus 0 sigma x 0 plus 1 sigma x 0 plus 0 sigma x 1 divided by half. Okay. Now sigma x, remember, is a matrix which looks like 0 1 1 0. Okay. So this is 0, but this is 1 and this is 1. Okay. So sigma x does have some non-zero expectation value in this state. On the other hand, if you compute the expectation value of sigma x in this state, you will find that that is 0. Because sigma x looks like 0 1 0 0. Okay. So you compute the trace of half half with 0 1 1 0, and you'll find that that expectation value doesn't click at all. Okay. So the expectation value of sigma x can differentiate between this pure state and this state. Same for the expectation value of sigma y. Okay. Well, maybe sigma y in this case might give you 0 in both cases, but sigma x in this case can differentiate between this pure state and this mixed state. Yeah. Is this point clear? What I said? Yeah. Okay. So what I was saying was that you can have, when we have a state of this kind, which is a linear superposition of two eigenstates, we sometimes say with probability half the state is in 1, and with probability half the system is in 0. Okay? However, what we mean is something a little more subtle. What we mean is the wave function is a superposition of being in 1 and 0. Okay? And so it is, if you measure something like sigma z, then it is indeed true that you get this answer with probability half and this answer with probability half. Okay? But you can measure other operators which will see the fact that you really have a superposition of this state and this state, which will see some cross terms between this state and this state. Like this operator sigma x. Are you familiar with the operator, the polyspin matrices? Okay. On the other hand, there is another kind of classical thing you could ask, which is, imagine that you really have a cat, the cat is in a box, okay, or there's really a bit and the bit is in a box, and it's either probability half, either it's up or it's 1 with probability half, or it's 0 with probability half, but it's in one of those states. So it's either definitely in 1 or it's definitely in 0 with probability half. You just are ignorant about which one it is. That kind of a probabilistic mixture you represent by means of a density matrix, which is this density matrix. Now, what is these two look like they are the same superficially, but they are not actually the same because some observables can distinguish between this density matrix and this pure state. Okay. And an example of an observable that can distinguish between them is this observable sigma x, whose expectation value in this state gives you some non-zero answer, but whose expectation value in this state gives you 0. Do you see that? Is that clear? Okay. So, pure states are sometimes we use language which makes them seem like they're probabilistic ensembles, but pure states are fundamentally different from probabilistic ensembles. And mixed states are represented by a density matrix. These are what are called mixed states. You should think of them as classical superpositions or classical probabilistic mixtures of different quantum mechanical eigenstates. And pure states really correspond to superpositions of this kind. Okay. So a mixed state is something that can't be written in this forms. It can't be written as the outer product of a wave function of this kind with itself. Okay. Okay, good. Is this point clear? Okay. So now what I want to ask is, so you might say, well, mixed states are different from pure states. And in fact, one of the tacit arguments, just to relate this to what I was saying, one of the tacit assumptions in Hawking's original derivation of the paradox was, look, we derived an expectation value which looked like it came from a mixed state. So is this density matrix a pure state or a mixed state? It's a mixed state. Right? This density matrix is a mixed state. In fact, it is precisely the state where you think of a superposition of all possible energy eigenstates, but with a probability that's proportional to e to the minus beta e. Okay. So it's a probabilistic superposition of all of those energy eigenstates. It's a mixed state. So, by computing this expectation value, it looks like we have got a thermal mixed state. And, another way to frame the paradox is to say that imagine that you started with a pure state when you formed the black hole. Then it looks like the evolution of the black hole by means of the formation, the emergence of that isometry, and the calculation you did has led you from a pure state into a mixed state. Okay? And that kind of evolution is obviously inconsistent with unitarity, because you can check that unitary evolution always takes a pure state to another pure state where you've just multiplied this with the time evolution operator u. Okay. Yeah.
You extremis polyphony partial base of a pure state by skirting an unseen system.
You can do that. You can think of it that way, or you can think of mixed states as fundamental. If you like, you can think of this state as being entangled. So if you wanted to do it that way, you would take this state and you could entangle it with another spin, and then if you took the trace, you would end up with this density matrix. Okay. So the point I wanted to make so far is just, you have these two different kinds of states, pure and mixed states, and you can distinguish between them. Just because they use the same language sometimes shouldn't confuse you. Okay? And the Hawking paradox, I'll come back to the Hawking paradox, but the Hawking paradox can be framed by saying, look, a pure state went by time evolution into a mixed state. And that looks like a paradox. Yeah. Yeah.
With USA, it is so when in our tech regression, this is
Yes. So I didn't understand exactly the question. For a pure it cannot go to a mixed state under unitary evolution. That is correct. However, in the case of the black hole, what Hawking was arguing was, look, it looked like we started with a pure state and we ended up with a mixed state, but there's no environment. There's only the black hole, right? There's no environment we talked about. So it looks like this is inconsistent with quantum mechanics. That's why it was a paradox. No, but there was no outside. Remember the way we described it, we said that we have a black hole and there are some fields. And then you start with, the black hole formed from collapse, and then you get some fields. And then I went through this derivation where I showed the Stephen Boltzmann law and how the black hole evaporated. In the end, you had only the fields. So there was no environment. We were keeping track of all degrees of freedom. It looks like we were keeping track of all degrees of freedom. Okay, all these arguments are wrong, by the way. That's why I've underlined seeming. So these are all wrong arguments. But, it looks like we've kept track of all degrees of freedom. In which case are you talking about? Sorry. Sorry. I'm making two separate points. Here I was going back to this point 4, which was, I was saying that the paradox of Hawking was that it looked like a pure state evolved through the black hole evolution and evaporation into a mixed state. Here what I've said is purely kinematic. I was just explaining there are two kinds of states which are pure states and mixed states in quantum mechanics. Both those kinds of states exist. And then I said the relation to the paradox is that in Hawking's paradox, it looked like a pure state evolved into a mixed state, which is inconsistent with unitary evolution, because unitary evolution always takes, and this is another pure state, okay, where U is the time evolution operator, independent of yeah. Yes.
Each is time.
It doesn't matter actually, as if it's unitary. Okay.
How come?
Well, we'll come to how we can explain the paradox. Right now, I only said that there are two kinds of states, and you know, so the only reason I was making reference back to the paradox was I was pointing out in this language that I just introduced, the paradox was that pure states went to mixed states. I didn't say it that way in the last lecture because I had not explained the notion of a pure and a mixed state. Okay, so is this notion clear? Okay. As I said, today for some time I just want to discuss this question. Okay, so we're not discussing the paradox for some time. Forget about the paradox. Just a statistical mechanics thing. We'll come back to the paradox. Yeah. Okay, good. So I now want to ask this question. So what do I mean by this question? Here it looks like pure states are not very close to mixed states. If you gave me this system of a cat or this system of a qubit, which has two different states, this pure state is not very close to a mixed state. It's not very close because look, I measure sigma x, I immediately get a different answer. Okay, good. So now I want to ask a slightly different question, right? So this was a system where there were only two states. Now, in the case of a black hole or in the case of many other statistical systems, we have many states. So consider a system with many energy eigenstates. What's an example of such a system? No, any system. So harmonic oscillator is one example of a system, but in fact, I want to think of an example of a system which has like the air in this room. Okay? If you think of the air in this room, any statistical system is a system which has a very large number of energy eigenstates. In fact, the harmonic oscillator, it has energy eigenstates, but the energy eigenstates are not, maybe I should make this more precise. Okay, in a band of energies, delta E. Okay. So like the systems Ashok is talking about which have a large entropy are systems of this kind. They have a lot of entropy. We are not counting maybe all of them are at zero energy in some sense, but there are a lot of states. Okay. There's also one more difference here, which is that the energy eigenstates here don't need to be degenerate. Okay, so there are just a lot of states. So between the energy E and E plus delta E, we imagine there are E to the S states. By the way, this S is the entropy. Okay, this is how the entropy is defined. One definition of the entropy is you look at the number of states between E and E plus delta E, and the number of these states is defined as the entropy. Okay, the density of states is defined as the entropy. Okay. So imagine that we go from E to E plus delta E, and in this there are E to the S states. There are many examples of such systems. As I said, any statistical system, any system with a lot of degrees of freedom has this property. Okay. Now, in this system, I want to consider two kinds of states. One state is what's called a mixed state. So, there are E to the S states. I'm going to call them EI. EI runs over all these different energies. It just labels all the different energy eigenstates. Okay. Have any of you seen this mixed state before? Yeah, it's the microcanonical ensemble. So this mixed state is the state that corresponds to the microcanonical ensemble. If you take this state and you compute expectation values of operators in this state, those will correspond to the expectation values of operators in the microcanonical ensemble. Okay? And a standard result in statistical mechanics tells you that those expectation values And these expectation values computed in this canonical ensemble are closed after corrections that are suppressed by 1 over square root s. But if you look at, it's convenient for us today to consider this microcanonical ensemble, which is just, which is a particular mixed state where you take all the energy eigenstates in a given band of energies and you take them to appear with equal probability, and the equal probability is 1 by e to the s. It has to be 1 by e to the s because the total probability has to be 1. Now, you might be confused why I took equal probability rather than taking probability with temperature, and that is because this band of energies is assumed to be narrow compared to the average, the width of the energies. Sorry, compared to the mean value of the energies. Okay? So the width of this energy band is taken to be narrow compared to the mean value, and that's why it's acceptable to say that this mixed state where all the energy eigenstates appear with equal probability is in fact gives you the same answer as that kind of a mixed state up to good accuracy. Okay? Nevertheless, for now, let's just consider this particular mixed state. Okay, you have a question? Or? Okay, so this is a mixed state. Now, I also want to consider in the same system a pure state. This is a linear superposition of all of these different energy eigenstates with some coefficients ai. Okay. Now, I can take the AIs to be any set of coefficients provided the state is normalized. Okay. So provided I ensure that the total state is normalized. Right? Now, there are many such states. In fact, there's an infinite number of such states because I can take the AIs to be whatever I like. Okay. So, this is an example of a pure state. The question I want to ask today is, if I take a typical pure state, and I'll explain what typical means. This is an important notion that appears many times when you discuss these questions of black hole information and so on. If you take a typical pure state, how close are the expectation values of observables to this microcanonical ensemble? Okay. So the next notion I need to define is the notion of a typical pure state. Okay, you're not able to see at the back? Uh, okay, I'll try and write on the top half. Yeah. I was just instructed that the line you can see below the line. That's why I erased the line. No, but I think Ahmed just told me it's okay to write below the line also. Where is Ahmed? He's not here to take responsibility for his actions. Okay, fine. Anyway, I'll try and write. Yeah. Okay. Never mind. Okay, so I'll try and write about. Yeah. Okay. So what is it? So I have to now introduce the notion of a typical pure state. Yeah. So take an expectation value of some operator. Without loss of generality, we can take the operator whose expectation value we want to take to be a projector. Do you know why in quantum mechanics it's only expectation values of projectors that are important? When you talk of observations? Yeah. Exactly. Because, the only thing that matters is that when you make a measurement, what the Bond rule tells you is you get different eigenstates and with an eigenvalue that's determined by with the probability that's determined by the expectation value of a projector. So what you really measure always are expectation values of projectors. Now it might be that one eigenvalue is 10,000 and the other eigenvalue is 0, but that's just how you chose to write your eigenvalues or how you chose to calibrate your meter. What is really physical are expectation values of projectors. So what I want to ask is, what I mean by typical pure state is you take the expectation value of a given projector, which can be any projector. It can be any projector in that system. But you don't take it in one state. Rather than taking it in one state, you integrate it. You take this expectation value and you integrate it with a measure, which I can call dh. And how do you define this measure dh? Well, you just define it to be the product of d2ai, okay? And then you put a delta function and you put a normalization factor. I'll see if I have the normalization factor in my notes. It doesn't matter actually what the normalization factor is. The normalization factor you put at integral of dh is 1. I do have it in my notes. So this n is chosen so that is equal to 2 into pi to d. Okay. What the value of this n is unimportant. What's important is that integral dh is equal to 1. Okay. So you said integral dh is equal to 1. And so this is what I mean by a typical pure state. Okay. So notice what I've done. What I said is I take the expectation value of a projector. Okay. But I take the expectation value of a projector not in one state, because one state could have some specific projector, and I could have some specific values, expectation values that are large, atypically small. But rather I take this expectation value and I average it over all pure states. Okay. So this I'll call the expectation value of P in a typical pure state. Let's call it double expectation value of P. Okay. Do you understand what this notion means? Usually you're used to taking a notion where you take the expectation value of the projector P in a given pure state. Okay. But say you don't know which pure state it is in, right? Or say you want to ask, what about a typical pure state? Then what should you do? You take the expectation value and then you average over all possible pure states. Why did I average over all possible pure states? Why is this the correct average? Because all I'm saying is, I'm allowed to take any coefficient I like. This D2AI is just because all those coefficients are complex numbers. That's why it's, every coefficient is a complex number. Provided I ensure that the state is normalized. So there's a constraint which tells you the sum of mod of AI square has to be equal to 1. Any choice of complex numbers with the with that meets the constraint that the sum of mod of AI square is equal to 1 is sufficient, gives me an example of a pure state. Okay. Therefore, what I mean by typical pure state is I take the expectation value of this projector P and then I just average over all of these states. This measure, by the way, is called the Haar measure on pure states. Okay, that's why I'm using the symbol H. Okay. Okay, is this clear? So this is what you mean by the expectation value in a typical pure state. So what we want to compute is the expectation value in a typical pure state minus trace of P and rho pure, rho micro. Okay. So the question that I asked there, the quantitative thing that I want to compute is this. I'm sorry, my rho and P all look the same, but it's a sign of if you're paying attention, if you can disambiguate them in your notes. Okay. So this is P and this is rho micro. That's the rho micro that I wrote there. Okay. So the quantitative translation of this question is, I want to look at this expectation value of a projector P. Why a projector P? Because those are the physical measurements you make in quantum mechanics. Okay. And then subtract off, compare that with the expectation value of this guy. Okay? With the expectation value of P, the same projector in this microcanonical ensemble. Okay. Okay, is this clear? Are there any questions about this? Yes. Yeah, it is written here. It's rho micro. It's this density matrix. Is defined here. P is the projector. P is the projector. Maybe I'll put a hat on the P. P is a projector. And I'm taking the expectation value in a pure state and I'm averaging over all pure states. That's my definition of the double expectation value. You get it by demanding this, that integral of this is 1. So what you have to do is you have to do the integral of this measure with just 1. And if you do that, then you find that n is this. Actually, I can't even completely promise you that all the factors are correct. There might be a factor of 2 off. I think this is correct, but you should check by doing this. It's just an integral of doing this integral. Yeah. Okay, good. So let's try and compute what this expectation value is. So what is the expectation value of P in one of these states, right? So what the expectation value of P is given by, so, I wrote there the bra for rho pure. I can also, so I wrote there the ket, I can also write the bra. And the bra is just given by right? So if I look at this expectation value, you can see that this is given by is this right? Is everyone happy with this? Good. Now I have to compute the now what do I have to do to compute this double expectation value? I have to take this guy, I have to integrate it with dh. Okay. Good. Now notice what dh is doing. Dh is doing an integral over all of these expectation values, uh, subject to the constraint that mod of sum of ai square has to be 1. Okay. However, notice that every time you satisfy this constraint, okay, so first consider this sum is over both I and j, okay, and both I and j run from 1 to e to the power s. Okay, remember that? Good. Now remember that every time you satisfy, consider the case where I is not equal to j. Imagine that you have satisfied this delta function constraint, which is the delta of sum of ai squared is equal to 1. But I is not equal to j. You can just flip the sign of aj, take aj to whatever it is, okay, to being minus or whatever it is, and you'll get another configuration of the AIs that also satisfies the constraints. In this measure, that configuration also contributes with the same measure, with the same weight. Okay. Therefore, you see that this integral must be proportional to delta ij. Do you see that? And this must be this sum. There's a sum over delta ij, but this sum, I'm just doing the integral, I'm interchanging the sum and integral, must actually be proportional to delta ij. You see that? And then what can it be when you're summing something is proportional to delta ij? Well, then it must be ei pei. Okay, because it's, maybe I'll write it a different way. I'll just collapse the sum in the first place. So it must be okay. And this is now integrated with the Haar measure. You have only one sum. Earlier you had two sums, but in fact all the terms with I not equal to j do not contribute. Do you see why? So only the terms with I equal to j contribute. Therefore you get this expression. Okay. In this expression, the only thing that depends, that h and a, h knows about is a. H doesn't know about ei and p. Ei and p don't have anything to do with the Haar measure. The Haar measure only knows about a. Look, the Haar measure is written here. Okay. So you can write this as sum of I, okay, ei p ei, into an integral. Okay. What is this integral? Can one of you guess what the value of this integral is going to be without actually doing it? Well, okay. The integral of sum of ai squared is 1. Okay. So it is true that the integral of sum of ai squared is 1. Yeah. Is what? But remember, here you're not doing sum of I e to the ai square. Here you're doing sum of I with ei pei. However, you're right that the constraint is forcing sum of ai squared to be 1. Okay? And all the AIs are democratic, right? This measure is treating all the AIs democratically. You see that? No AI is special. Therefore, if the sum of ai square is 1, this integral has to be 1 by e to the power s, because there are e to the power s AIs. Okay. Therefore, this becomes, oh sorry, I'm writing below again. Let me go to that board. The what? Yeah, what I said about the AIs is this integral can't depend on the value of I. It can't depend on the value of I. It can't depend on the value of I because the integral of this with this Haar measure. This Haar measure is written here, but this Haar measure is completely democratic in all the AIs. It doesn't favor one AI or the other AI. Therefore, whatever this integral is cannot depend on the value of I. It must be the same for I equal to 1 as it is for I equal to 10, as it is for I equal to e to the s. And you also know that sum of ai squared has to be 1. So sum of ai squared has to be 1. right? Therefore, this integral has to take the value 1 over e to the s. This value has to be 1 by e to the s. Okay. Therefore, what we have right now shown is that the double expectation value of p is given by where this sum runs over all energy eigenstates. Do you see that? Why did I get 1 over e to the s here? It is because the sum of ai squared over I equal to 1 p e to the s is equal to 1. And all the ai squares, so the sum of the expectation value of ai squares is also equal to 1 because this is constrained under the Haar measure. So if I integrate this with dh, I still get 1. There is a inside dh. So, but remember that sum of ai square is equal to 1 independent of all the a's. So this is just equal to 1, right? This is just 1. It's another way of writing 1. So what's integral of dh with this? It's also 1 because remember integral of dh is 1, right? Therefore, sum of I integral of dh with mod of ai squared is equal to 1.
So it's essentially sum over PP power S number. So
Yeah.
it's very space there is.
It has no closely spaced here. There's a closely spaced was not important here. Whether they're closely of
Function.
well, for that it was important, but in this integral it was not important. Notice here. Do you see this? That integral dh of sum of ai squared is equal to 1. Is a step here? Because integral dh is 1. Therefore, sum of I can interchange the sum in the integral. Sum of I integral of dh mod of ai square is also equal to 1. Okay. But this answer cannot depend on I. So let this answer be some number. Let's call it C. So sum of I into C is equal to 1. So what is C? C has to be 1 over how many terms you summed over. The number of terms you summed over is e to the s. Therefore, C was 1 over e to the s. Yes. Okay. So the double expectation value of P is this. Okay, this is what we just showed. Yeah, is this clear? Good. Now, what about the expectation value in this microcanonical ensemble? Well, that's actually pretty easy to compute. It's written here almost. When you take the trace in a density matrix of this kind, all you do is you put a P here and you flip this. Right? You take this ket that you have and put it on the other side. That's how you take the trace in a density matrix of this kind. So trace of P that I was P hat. So I'm sorry, my handwriting is too bad to distinguish P and rho. So I'm going to put a hat over P where I can. I'll try and remember to put a hat over P. Yeah. So what is trace of P hat? Well, it's just taking the trace in this, but it's also the same. Okay. Okay. So what we found is that in a typical pure state, the expectation value of any projector, I didn't have to specify which projector I was looking at. The expectation value of any projector is the same as the expectation value in the microcanonical ensemble. That's what we just showed. Yeah. Okay. Now, this proof is a little bit deceptive because in this proof, I didn't even use the fact that e to the s was large. So in the example that I gave you earlier, where I said that, you have a two-state system and you have sigma x and so on, this proof even holds there. It even holds there, and all it tells you is when you look at a typical pure state, like taking the expectation value of some operator in a pure state and averaging over all pure states, is basically the same as taking the microcanonical ensemble. And you might say, well, okay, that's not so surprising. Okay. But in any given pure state, there's a lot of difference between the microcanonical ensemble and the pure state. Okay. So we are now going to compute one more quantity to answer this question. And that quantity is we are going to compute the standard deviation. We are going to compute how much the expectation value in a pure state differs from the mixed state if you square an average. Okay. So that's the first result we got. Okay. So these two are equal. Okay. This is the first result we proved. Okay. Okay. Good. So now I'm going to compute something slightly different, which is I'm going to compute the expectation value of psi pure p hat psi pure p hat. Okay. So let's say you came to me and you said, whatever, this result is deceptive because what you said is you could either take the density matrix, which was a democratic combination of all these energy eigenstates, or you could take the expectation value in a pure state average of all pure states, you'd get the same answer. So now I want to compute something slightly different, which is this. Okay. This quantity is the expectation value of p hat, this projector, in the pure state, minus this mean expectation value, but squared and averaged over the Haar measure. Okay. So this is giving me a measure of how much a typical pure state. So we already showed that the expectation value of the projector in a typical pure state is the same. But now we want to ask, is this expectation value the same as the microcanonical ensemble? Because there are lots of deviations, large and small. Okay, lots of some positive deviations, some negative deviations. Or is it that the deviations are uniformly small? And so to compute that, we are now going to look at the expectation value of the pure state, of this projector in the pure state, minus this expectation value and square it and integrate it over the Haar measure. Why is it good to square this? Because this expectation value is some real number, and so you square it. This is everywhere positive. So earlier, if those two expectation values were turning out to be the same because there were lots of positive and negative deviations, this expectation value will detect that. If this turns out to be large, then we know that actually pure states are not really like mixed states, but rather sometimes they are very different in one direction and sometimes they're very different in the other direction. So that's the possibility that we want to check. Yeah, this is the variance exactly. Huh? What? Well, so right now what we showed is that the expectation value of a projector in a typical pure state was the same as the expectation value in the microcanonical ensemble. Now that doesn't rule out the possibility, because we averaged over pure states, that some pure states have very different expectation values in the positive direction and some pure states have very different expectation values in the negative direction, and it's because we are averaging that we are getting zero. So this will detect such a probability if it occurs. If I tell you the expectation value of A is the same as the expectation value of B, it doesn't tell you that A and B actually are close as random variables. You have to also check the deviation of A minus B. So you have to see so it could be that A is just sometimes positive, sometimes negative. So that's why I'm squaring here, and I'm going to check this also. Yeah. Okay, good. So let's compute what this is. So we just have to do this whole procedure. Let's stop writing. So it's basically just that calculation that we did. So this is the integral. Oh, is this too thin, or can you see? Is there another one which writes? It's right better. Okay. Okay, this is writing fine. See? So this is EJ P hat EI. Okay. EI AJ star. Remember, this was the basic term that we got, which should be written here still, or maybe it got erased. This was the term that we got when we took the expectation value of P hat in the pure state. Okay. We got this, remember the pure state is given by sum of AI, EI. So you take the cat and you get this AI, AJ star term in this way. Okay, this is coming from here. You see this? Okay. Now what about this? Well, this is actually the same. It's just with a delta IJ. So you can put a minus delta IJ divided by E to the S. That's one term of this kind. This is summed over IJ. And I have to take this and I have to multiply it with another term that looks the same. So you can see, if you do that, what you will get will be a sum over IJKL. And then you write so So this expression is going to be a little long, but actually it's a very simple expression. So please don't get confused. Okay. Okay. Do you see where this expression comes from? It just came from recognizing that I was just squaring this expectation value, right? So I can just write it twice. Okay. This is one bracket and this is the other bracket. Okay. So this bracket, notice it gave you expectation value of EJ P hat AI into AI AJ star. That came from here. And then there was this microcanonical ensemble, but that's just this expectation value with the delta ij by e to the s. You see, because that comes from there. Similarly for here, except I'm using different dummy variables, I have EL P hat AK and then AK AL star minus delta KL by e to the s. Okay. Is this clear? Okay, good. Now notice we have an we have this I've written two Haar measures. I don't need two, just need one. We have this integral over the Haar measure, and by the same kinds of arguments that I gave you previously, it must be the case that either I is equal to J and K is equal to L, okay, or I is equal to L and J is equal to K. Okay, by the same kinds of arguments that I gave you previously. There are only two terms that contribute to this. So there are some terms that contribute as I equal to J, K equal to L, okay, or I equal to L and K equal to J. Okay. Now I have here, in fact, the full answer for this integral, which I'm not going to derive, but in fact, this is just a question of taking this measure and deriving what this expectation value is of AI, AJ star, AK, AL star. Okay. So you take this measure, which is D to AI, and you have to do an integral where you derive this expectation value of AI, AJ star, AK, AL star. Okay. It's not so hard to derive it. The way you would derive it is you write this measure, as e to the I theta into sum of AI square minus 1 integral of d theta. And then you can compute all of these expectation values, okay, in a straightforward way. I'm just going to quote the answer for the expectation value. And the answer I can write here. Hold on. Okay, so the answer is okay. Okay, this answer I don't want to spend time deriving because it's an exercise basically in calculus of many variables. So given the Haar measure that I just erased, but hopefully you have in your notes, you can take this answer and derive with respect to that delta function constraint this kind of expectation value. Okay, it's not that hard to do. I'm happy to do it with you out of this thing, but this is the answer that you'll get. Okay, so as I said, either I is equal to J and K is equal to L, or I is equal to L and J is equal to K. And then the expectation value is divided by 1 by e to the s into 1 by e to the s plus 1. Yeah. Yeah. The projector operator has not appeared here. Yes. Is it back and the yes, yes, yes. It's also yeah. Yeah. Yes. 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 Isn't it a what interaction? It is an event, but sorry, why is that relevant here to what we are saying? It is true that if you to make this measurement, you have to turn on some apparatus. and make the system interact with the apparatus. If you're thinking about the paradox, we'll come to that paradox later. Right now, I'm asking a question which is in statistical mechanics, how close are pure and mixed states? Okay, so we'll come back to the paradox if that's what you're worried about. The question is, if I'm given a statistical system, I'm given a system. It's a system of qubits. It's a quantum computer, something. And I have not told you if it's in a pure state or a mixed state. And I make some observations in the standard way in which you make observations in a quantum computer and any other system. Okay. Then I'm trying to ask if the system was in a pure state or if it had already interacted with the environment previously before I made my measurement, so that it was in a mixed state. Will I get different answers or will I get the same answer? Right now, we found that the expectation value of any observation you make, any projection you make, will be the same if you take a typical pure state and the microcanonical ensemble. Okay. Now, that could be deceptive because I said that, it could be the case that the expectation values in pure states are different and fluctuate a lot. And that's why you get the same expectation value. And so we are now computing this variance. And so the question here is just a statistical mechanics system. Let's say you enter this room and you asked, is this room is in a pure state or is it in a mixed state? What will you do? You'll make some measurements. The question is, will you get different answers in those two cases or not? Okay. So that's what we're doing here. So this is the exercise right now is, this could be a StatMech lecture. It doesn't have to be a black holes lecture. I'm going to relate it to black holes, but right now it could be just StatMech. Yeah. So I hope this is clear. This exercise we are doing is clear. It's an important exercise, okay, because this, to know this actually is already a step forward in understanding many questions about black holes. Yeah? Okay, good. So now you can actually persuade yourself that in fact it's this term that's important. Okay. So this term that you have, there's a delta ij, delta kl term. Okay, there's a delta ij and a delta kl term. And you can persuade yourself with some exercise that this term, by the way, I gave you the expectation value of this product of 4 operators. There's also the expectation value of products of 2 operators that you will get. When you expand this out, you'll get ai aj star into delta kl. That will give you another term that's proportional to delta ij. You see, you'll also get AKAL star into delta ij. That will also give you a term that's proportional to delta KL, as we discussed. So you'll get lots of terms which are proportional to delta ij, delta KL, not just from this 4-term expectation value, but also from these expectation values. And from here, okay, when you get these cross terms, you can check, it's pretty easy to check that these cross terms always contribute with a negative sign when you expand out the term. Okay. So you'll get some cross terms and they always contribute with a negative sign. So this expectation value is smaller than the contribution that comes from, this is a positive term, right? This whole thing. So I'm just trying to bound it above, and it's pretty, you can compute the whole answer, but I'll just give you, it's simple to look at this answer. It's strictly smaller than the delta IL delta JK term. Okay. And the delta IL delta JK term yeah. S into, oh, am I again going below the line? Sorry. I'm just trying to continue the equation from here. Can you see up to this line or not? This is also hard to see. It's hard to see or it's possible? It's hard to see. It's okay. Okay, maybe I okay. Okay, I'll erase this then and I'll write the expression. Okay. There's another point I want to make. It's too bad I had to erase this. Okay, I'm continuing the equation from there. This is smaller than the term which has delta IL and delta JK. Okay. By e to the s into e to the s plus 1. Okay. Now notice what happens with the term which has a delta IL and a delta JK. Okay. So in the case where you have a delta IL, this term is equal to this term. Okay. And this term, this J is equal to this K. You see this? Okay. Okay, good. So it's smaller than this. And so what you get here is just a sum. It's smaller than EJ PEI into EL E hat EK. Okay. This e to the power s into e to the power s plus 1 came from the term that I raised in the previous line. Remember, I had given you the expectation value of the 4 terms. So I had an e to the power s into e to the power s plus 1. I also had a term which looked like a delta ij and a delta kl. But if you expand it out, it's a good exercise to do. You'll find there are lots of terms that are proportional to delta ij, delta kl. There are actually 4 terms. There is the term that comes from this 4 term expectation value. There is the term that comes from this cross term. There is a term that comes from this cross term, this one and this one. And there is the term that comes from multiplying the delta ij, delta kl together. And it's easy to see that totally they'll give you a negative sign. Okay? So that expression, whatever it is smaller than this. It's a positive number and it's smaller than this number. Okay. But notice that this number itself that you have, okay, is when you put I is equal to L, that's like summing over some set of states. It's putting this is equal to this. Okay. So you're summing and the sum, now you only have this delta function. This e to the power s into e to the power s plus 1 comes out outside. And all you have here is 1 by e to the power s into e to the power s plus 1 into sum of, let's sum over now only 2 variables, JNI, EJ, P hat, EI, EI, P hat, EJ. But now remember that when you sum over JNI, when you sum over this complete set of states, this is like, this sum that you have is always smaller than the expectation value of P squared. What you're doing here is you're taking a trace, okay? You've put a complete set of states here, but it's not quite a complete set of states because you summed over a microcanonical ensemble. So you're not summing over all states in the Hilbert space. So this basis, if this was just a sum over all states, then this would just be the insertion of the identity, and you would get P hat squared. In general, you get something that's smaller than P hat squared, but remember P hat squared itself is P hat squared itself is P hat, right? Because P hat is a projector, right? And the expectation value of P hat in any state is smaller than 1. Right? So this whole thing is smaller than 1 by e to the s plus 1. How did that happen? Because remember, you are summing here. Okay? This is like inserting a complete set of states. So I could have replaced, so this is like, putting just a P hat squared, just like getting rid of this. In fact, there's an inequality here because you're not inserting quite a complete set of states, but little less than a complete set of states. Remember, P hat square in any state of EJ has to be smaller than 1. So you're summing over e to the s terms, each of which is some number smaller than 1. Therefore, this whole expression is smaller than 1 by e to the s plus 1. Okay. So you see that we have derived that this whole expression is smaller than 1 by e to the s plus 1. Okay. Now, this is actually a very strong result because what it tells you is that if you look at a system with a large entropy, then this number is very small. So, not only have we derived that the expectation value of P hat is equal to this, we have also derived that rho pure, so this is the second result which I am writing here, rho pure minus trace of rho micro, the whole squared is smaller than 1 by e to the s plus 1. What that tells you is that not only the expectation value of P hat, so I'm now going to write a slightly imprecise equation. So far, everything we've derived is precise. What this tells you is that, sorry, not rho pure, psi pure. Sorry. So now I'm writing an imprecise equation, but it's the equation you should keep in mind, okay? Okay, this equation is actually not a very precise equation, but it's the equation you should keep in mind. What we derived here is that if you take a typical pure state and you look at the expectation value of p hat, it is almost like the expectation value in the microcanonical ensemble. Up to a typical deviation, the deviation depends on which state you're in, but the typical size of the deviation is always of order e to the minus s by 2. Why e to the minus s by 2? Because this was the square of the deviation. The square of the deviation was 1 by e to the s. Therefore, the typical deviation is order e to the minus s by 2. The 1 here doesn't matter. Okay. So, what we have shown is that not only are typical pure states like mixed states in terms of the expectation value, but that the deviation of any observable in a system with high entropy between a pure state, a typical pure state, and a mixed state is small, and it's so small that it's suppressed by order e to the minus s by 2. Okay. So, unless you make measurements which are accurate up to e to the minus s by 2, you cannot differentiate a pure state and a mixed state. Okay. This is a very important result in this whole story. And if this is not clear, please ask me. I'm going to write one more bullet point here. This is the bullet point for today's talk. And then just that pure and mixed states are the same for any observation. Okay. For any observation, or typical pure and mixed states are the same for any observation. Okay. I'm going to say some more things. Yeah. But go on. Yeah.
So basically, why did you take a projectional operator instead of just taking Hermitian matrix?
You can take any Hermitian observable, but what I wanted to say was when you take a Hermitian, you see, you can take a Hermitian operator which is 100,000 times into the projection operator. That doesn't mean anything. It will not tell you that pure and mixed states are different. What you measure in quantum mechanics are always expectation values of projections. Even when you measure a Hermitian operator, what you really see are the different eigenstates appearing with an expectation value that's given by the expectation value of the corresponding projector. So the Born rule in quantum mechanics tells you take the Hermitian operator, you do a spectral decomposition, and when you do a measurement of the Hermitian operator, you don't get the expectation value. Rather, what you get are the different eigenvalues with the probability that's given by the corresponding projectors.
Operators, we do not have the condition PS also.
No. That was not important here. What I showed here is that the expectation value of a projector is the same. And the reason for that is you could take a Hermitian operator which looked like, okay, let's say I had two systems, okay, and the probability of a measurement in one was the same as the probability that you'd get the other 99.99% of the time. Okay. So you would say that those two systems are the same. They're very close to each other. Good. Now let's say I define my measurement to be 10 billion into 10 billion if you get some answer and 0 if you get some other answer. In that case, even though there's only some 0.0001 possibility of getting a different answer, because I multiplied my answer by 10 billion, I'll find the expectation value is different. But that's meaningless. That's because you chose to multiply your answer by 10 billion. So when we compare random variables, you always want to compare probability distributions and probabilities. You don't want to compare the fact that I chose to assign to a given outcome the value 10 billion or 100 billion because that's in your hand. Okay. So what you always want to compare are probabilities of getting different answers when you want to ask questions about close. So when you ask questions about close, you should always compare projectors. By the way, that being said, you can do this whole thing for an observable, and what you'll get here is order e to the minus s by 2 into the standard deviation of the observable. You'll get a factor here which gives you the standard deviation of the observable, but that's actually not a factor which is physical. I want to emphasize that when you compare whether states are close, you should look at projectors. Yeah. Yeah. Yeah, good. So I'll say that now. Mixed state was the microcanonical ensemble. So by mixed state, we meant a specific mixed state. But what I mean by non-typical pure, I'll say in a minute. That's a good question. Yeah. Yeah. We got the last line from the fact that the average of the variation was 1 by e to the s plus 1. Right? So I just said I took the square root because the average of the square of the variation was e to the s plus 1. The average variation is e to the minus s by 2. this is an imprecise statement. That's why I've written order of. It's not an equation. I mean, there's an order of here. So it's order of e to the minus. When you write order of, you don't keep track of ones. And so order of means, some when you have a large number and you have a parameter, here in this case, the parameter is e to the s, you can speak of order of magnitudes of terms. So the order of magnitude of the deviation is e to the minus s by 2. This is the exact result, yeah. Because you see, the typical deviation of a pure state and a mixed state is very small when you have a system which is very large, right? From this equation, the typical difference between this expectation value and this expectation value is very small. It's suppressed by e to the minus s by 2. That's how you concluded this. Up to order, it's the same. I've just written this in words. Is it not clear? Okay, is this point not clear? Okay, yeah. Yeah. Yeah, this is this is the precise result. Okay, if you guys want to be very precise, you can keep this result in mind. But what is this result telling you? If I take the expectation value of something, if I take the standard deviation squared, and I find that the typical deviation is 1000. The square of the typical deviation, the expectation value of the square of the typical deviation is 10,000. Then I would say the typical deviation is 100. That's all I've done here. Or if the square of the typical deviation is 1 by 10,000, I say the typical deviation is 1 by 100. That's all I've done here. Yeah? That's how this result is often stated. That's why I want you to keep this in mind. You'll often find that statement in the literature, not this statement, although this is the precise statement. Yeah. Yeah.
So whenever we are taking a projection,
Yeah.
operating on the pure state, concept is alive. So
No. Projection, no. Projections are standard things in quantum mechanics. When you make a measurement, you measure the expectation value of a projection operator. This is the basic postulate of quantum mechanics is when you make a measurement, you measure the expectation value of a projection operator. You are in fact operating on it with a unitary. The unitary that you need to act on it, this is the standard von Neumann theory of measurement, is you entangle an operator in the system with an operator in the apparatus. Okay, good. So now the question about what are atypical states. Yeah, so I want to answer that. So it's important here that we looked at typical states. Okay. For instance, what's an example of a case where this might be violated? Let's say I took a given pure state. Okay, here I was taking typical pure states, right? Let's say I take a given pure state, like some state which has like some particular values of AI. Like it looks like, I'm going to make up some values, okay? 10 to the minus 6 plus 0.34i into E1, okay, plus some other values, okay, 0.32 plus 0.16i into E2 and so on. Okay, let's say I take one particular realization of a pure state. I'm just making up these numbers, okay? And then I take the following projector, which is, do you see why this is a projector itself? It's a one-dimensional projector. It projects onto the pure state. Okay. If I take this projector, what is the expectation value of this projector in this state? It's 1. Right? So the expectation value of this projector in this state is 1. What is the expectation value of this projector in the microcanonical density matrix? Yeah, it's 1 by e to the s. Okay, it's just 1 by e to the s. You take this density matrix and you expect it to be 1 by e to the s. Okay, so now you could have said, look for this particular state and this particular projector, you found an answer that was very different. And that's true. So there are always some pure states and some measurements you can do that can distinguish a particular pure state from, a mixed state. But the picture that you should keep in mind, and this is maybe the important picture to keep in mind, is that if you think of the space of all states, think of the space of all states. The space of all states is actually a Hilbert space, but I'm drawing it this way because it's just convenient to imagine it as a manifold. So think of the space of all states. Then in this big space, it's some space with a big volume. There are some states which are atypical. So there are some states which are atypical with respect to a particular measurement. So let's say you decided ahead of time that I'm going to measure the temperature at this point. In most states, you will get the same answer for the temperature in a pure state as you would in a mixed state. But in some states, in some very specific states, of course, it could be that there's a big fluctuation, so the temperature here was much larger or much smaller. But the volume, those states themselves are very atypical in the space itself. So for most states, most states look almost featureless with respect to almost all measurements. Of course, there are some states which are atypical states with respect to a given measurements. But states which are atypical with respect to one given measurement are generally typical with respect to all other measurements. Of course, if you tune both the state and the measurement, then you might find an answer that's very different from the mixed state. So the fact that these are typical pure states is important. But typical pure and mixed states are the same for any observation up to order e to the minus s by 2. That's point number one. The second point is, this is a kinematic result. This result we derived was a kinematic result. We didn't need to use any dynamics. We didn't need to use that, for instance, the system was chaotic. We didn't need to use that, for instance, so this is a kinematic result. Sometimes you will hear in discussions of thermalization, the question of eigenstate thermalization hypothesis and so on. Those are all more sophisticated questions. This result is a very simple result. It doesn't rely much on the dynamics, the Hamiltonian, whether the distribution of energy eigenvalues is chaotic or integrable, nothing. It's a very robust result, which tells you typical pure states in a high-dimensional system look the same as mixed states, up to very high accuracy. Okay? So in this case, for instance, remember, in this room, for instance, the entropy itself might be 10 to the 26. So this, what this is saying is, if I take this room and I take a typical pure state, for almost any quantum mechanical measurement you make, the answer will be the same up to e to the minus 10 to the 26. Okay? And of course, there are some states which are atypical, but many are not. And this is a very robust result. I don't need to know the Hamiltonian of the gas in the room to derive this result. Okay? So it's a kinematic result. The second thing is, some of you might be confused by, is that let's say you measure something like the entanglement entropy. Okay? And what is the entanglement entropy? So what is the von Neumann entropy for the pure state? It's 0. What is the von Neumann entropy for the mixed state? Yeah, so in this case, it's just S, okay, for this mixed state. It will turn out to be S. If you compute what the von Neumann entropy is for the mixed state we've been considering, this micro state, you'll find the von Neumann entropy is just S. Okay? So you might say, look, I measure the von Neumann entropy and I get a very different answer. I get 0 for the pure state, I get S for the mixed state. And that is because the von Neumann entropy is famously not the expectation value of any observable. Okay? The von Neumann entropy can differentiate between mixed states and pure states. So, for instance, the von Neumann entropy can differentiate states mixed and pure states. Okay. However, the von Neumann entropy is not the expectation value of any observable. Okay. It is not directly an observable. Rather, to construct the von Neumann entropy, you have to make many different measurements and then you have to combine them together to be able to construct the von Neumann entropy. So the von Neumann entropy of a system is actually a pretty sensitive quantity for a big system. If you give me a big system and I have to measure its von Neumann entropy accurately, it is true that if I do measure it accurately, in the end, I'll get a different answer for a mixed state and a pure state. But what these results are telling you is that you'll have to make a lot of intermediate measurements accurately and then reconstruct the von Neumann entropy from that. Okay. So the reason our result doesn't apply to von Neumann entropy is because the von Neumann entropy is famously not the expectation value of any projector. Okay. So this is what I mean here. It's not, so trace of rho log rho is not equal to trace of rho A for any A. You might think you take A equal to log rho, but that's not allowed. Okay, you have to take A to be some operator which is defined independently of rho. Okay. So there's no operator A that you can write down which is independent of rho that has the property that it gives you the von Neumann entropy. So the von Neumann entropy is not directly an observable. So that's the second thing to not get confused about. Yeah? Okay, so this is a point that I wanted to make. Now, can I take 5 minutes more or should I stop here and continue? What would you say? Okay, fine. Okay, so now I want to go back to the paradox and then I will say, I'm going to say more about this. Is this point clear? Okay, so far, almost everything I've said in this lecture is a StatMech result. It's a simple StatMech result about systems which have many degrees of freedom. Nevertheless, it's a result that you should definitely know because it's used all the time in the literature. And the result is, the bullet point is written there, which is the typical pure and mixed states. When I talk about mixed states, I mean a specific mixed state, the microcanonical ensemble. Maybe I can write it better. Typical pure and microcanonical states, mixed states. Sorry, I wrote microcanonical mixed states are the same for any observation up to order e to the minus s by 2. Okay. And it's a physical result. It's telling us that, you look at this system, you can't really make out from some simple observation whether it's mixed or pure. And this is not true for the simple 1-qubit system we started with at the beginning, because for that, S is just log 2. So you don't have a lot of degrees of freedom for that. Whereas you have a lot of degrees of freedom, then this is not true. Okay, good. Now let me say something, let me go back to the paradox, okay? And I'm going to say something about the paradox, and then we'll come back and we'll have more to say about the paradox. So, what was Hawking's argument? Hawking's argument was that, look, I kept track of this particular observable which we derived, which was the occupation number of this outgoing degree of freedom. And that outgoing number looked like it was thermal. And from that, we concluded that the state itself was thermal. However, what this analysis teaches us is that this calculation is not precise enough to lead to a paradox. This calculation is not precise enough to lead to a paradox because if the state was pure, you would still expect to get those same expectation values up to corrections that are suppressed by order e to the minus s by 2, where in this case the relevant s is the entropy of the black hole. And we didn't keep track of corrections that were even perturbative in the entropy of the black hole. Therefore, that calculation, the fact that you computed some expectation value and you got an answer that up to leading order was the same as a thermal answer, is not enough to let you conclude that the final state is really, mixed. Okay. So this is the point I want to make now, which is that Hawking's calculation is not precise enough to lead to a paradox. Now, I'll come back in the next lecture, which we have after lunch, and I'll explain how you can refine Hawking's calculation to get a more robust paradox. But just this calculation, by the way, this calculation is not precise enough to lead to a paradox. By the way, let me say something in defense of Hawking. Hawking himself didn't actually give this calculation as a way to get the paradox. Okay, this is how it's often explained popularly. And maybe Hawking also later started saying this in a popular way. But in fact, if you go and read the paper on the breakdown of predictability, he doesn't actually say, oh, you do this calculation and from here you get a paradox. Okay, he gives a slightly more sophisticated argument, which I'll explain after lunch. However, this is the argument you will find if you open a popular description of the paradox, which is you do a calculation of Hawking radiation. It looks like it's thermal. It looks like it doesn't depend on details of what went in. And that's a paradox. However, this is not a paradox because of the statistical mechanics result that we showed today. Okay. So it's not a paradox because pure states are almost the same as big states, and we didn't even keep track of 1 over s corrections. And therefore, this statistical mechanics result is already sufficient to resolve this version of the paradox. Okay. I want to say a few words about the small corrections theorem, but are there any questions about that? So far we are just saying something about StatMech, but given that we have a StatMech result, we can now apply it directly to the case of black holes. And we can say this argument that calculation told us there was a paradox is not sufficient. I'll have to give you a better argument for a paradox. We'll try and give a better argument after lunch. Okay? But this argument already is wrong. You can't just say I computed this and I got a paradox. It's not enough unless you can compute all corrections up e to the minus s by 2. Are there any questions about this part? Can I say something more? Okay. Or you want to? Okay. Okay. So since I might get questions over lunch, I'm going to spend maybe 5 or 10 minutes just saying something about the small corrections theorem of Samir Mathur, and then we'll come back and we'll discuss this more after lunch. Okay. Okay. So now many of you asked me that there's this so-called small corrections theorem of Samir Mathur that says that these kinds of small corrections where you say that. So, what was the point here? The point here was that you could always add small corrections which you didn't keep track of, right? And if you added these small corrections, then the answer would be perfectly consistent with saying that the full state was pure. Is this point clear? I could take this calculation and I could add some small corrections to it, and the statistical mechanics result we have shown tells us it's not a surprise that in a pure state you got this expectation value. You should have expected it, in fact. Okay. Is this point clear? I hope. Or not clear? I see a lot of blank faces, so maybe it's not clear. Okay. Okay, I'll go on. You can ask me again. We'll come back after lunch. Let me say something about the small corrections theorem. So there's this result by Samir Mathur which seems to suggest that this argument I gave you right now, which says that small corrections can unitrize the Hawking result, might not be correct. Okay. However, I want to point out that one has to be careful about the sense in which one uses small corrections. Okay. So in particular, the kind of example that Samir gives is the following. The kind of example Samir gives is, let's say you take a state which looks like, if you look at Samir's paper, you will find a state which looks like this to the power a. Okay, multiplied over many times. So you have states of entangled qubits which look like this. Okay, n times. And then Samir says the way you should model black hole evaporation is you pull this qubit out. So what is the density matrix of this qubit if you just pull out this qubit and integrate over this qubit? There's a 1 by root 2 here. And somebody says, some of you said this at the beginning. It's just half. Okay, if you pull out this qubit and you integrate out over this qubit, then this density matrix, rho, looks like half. It's the mixed density matrix that we discussed earlier. That's because if you have an entangled system of 2 qubits and I trace over 1 qubit, then on the other qubit will look like it's in a mixed state. Okay. So if you trace over this, you'll get a mixed state for this. Similarly for all the others. Okay. So if you just trace over all the first qubits and you keep track of only the second qubits, then you'll get a mixed state for the whole thing, which will look like this. And so on. Okay, n times. Now what Samir points out is that if you added small corrections to the state, to each state here, if you change this state with some epsilon corrections of the following kind, 0, 0, plus epsilon 1, plus epsilon 2, 0, 1, plus epsilon 3, 1, 0, plus epsilon 4, 1, 1. These are all possible small corrections you could add to this state. If you added small corrections to this state and then did the trace, you would still get a mixed density matrix, which would be pretty close to the density matrix you had here. Okay. So that is the small corrections theorem that some of you have heard of. It is that if you start with these EPR pairs and you trace out one pair, then you will find that the other pair is a mixed density matrix. But if you take the EPR pair, rather than taking exactly this pair, if you add small corrections to the state and then trace out, you will still get a von Neumann entropy for this second qubit, which is close to the von Neumann entropy you had earlier. Okay. In this sense, small corrections are not sufficient to convert the state of the second qubit from being a mixed state to being a pure state. Okay. So in this sense, if you take these qubits and you add small corrections to the state, then you cannot convert the second qubit state from being a mixed state to a small state. So it is important that small corrections does not mean, is not equal to the statement that that rho pure is close to rho micro as a state. You can measure the difference between two density matrices. One way to measure the distance between two density matrices is you take the density matrix of rho pure, which is just rho pure, take that state and look at trace. So for instance, one way to measure it would be this. You could look at rho micro minus psi pure squared. You could look at this trace of this thing squared. And this trace is not close to 0. This trace is not suppressed by e to the s. Okay, this is order 1. So what we have shown right now is that for any observation, a typical pure state looks the same as a mixed state. That does not mean that in the Hilbert space, a typical pure state is almost parallel to a mixed state. Okay? So you should be very clear about this. Small corrections doesn't mean that in the Hilbert space, where you could define the norm between a mixed state and a pure state this way, by looking at the difference in the density matrices, that the two density matrices are close as density matrices. That's not what is being said. What is being said is if you take a typical observation, that observation turns out to be the same. So please be clear about this point, which is that typical observations are close. This is the last point I want to make and then I'll stop. Observations are close. So I said they're the same. Typical observations, I'll say, are the same. But the states are not the same. All right, let me write out close, but the states are not. Okay, so the last bullet point I made is that I spent this lecture telling you that in a typical state, observations that you make will be the same as observations you get in a mixed state. That's very different from saying that the state itself, as a state in the Hilbert space, is close. Okay? And there's a difference between those two statements. So in fact, these states are almost orthogonal. If you want to ask questions of small corrections in this state, then yes, the corrections to the state that Hawking proposed are large. But that's very different from saying that any observation you make, like you make an observation of the outgoing mode number, or you make an observation of the 1-point function of the metric. Right? We are making observations all the time. We are measuring the metric here. So we don't expect that any such typical observation is very different. But because the state has so much information, because the state has so much fine-grained information, it's very different to say that the states are close and to say that typical observations are close. Okay. So maybe these points are not completely clear. In fact, it's not surprising because they haven't been completely clear to experts for a long time. But let me just end here, since I'm already over time, with the following statement, which is that everything I said so far just involved undergraduate quantum mechanics and statistical mechanics. So if you go back and you try and redo these calculations, you should be able to derive all of these points. And please try and make sure that at the end of the calculations you do, you're able to understand these bullet points. Okay, these are the bullet points. So those were the bullet points we made in the first lecture. And these are the bullet points I want you to keep track of today, which is that typical pure states are close to microcanonical states. This is a kinematic result. And close to microcanonical states doesn't mean they're close as vectors in the Hilbert space. So it doesn't mean they're close as density matrices in the Hilbert space. It just means for typical observations, you get the same answer. But the states are still very different. So and because Hawking computed some typical observations like the expectation value of the outgoing number operator, that calculation is not precise enough to lead to a paradox. And small corrections in that observable are sufficient to make it consistent with unitarity. Okay, I'm sorry for going over time. We can stop here and we'll anyway resume after lunch. So I'll stop here. Thank you, Peter.